Hello, welcome to the last lecture on generating functions. We will study in this lecture perhaps the most important application of generating functions in the context of computer science, that is for solving recurrence relations. Fine, so I will explain the general methodology using a few examples, and that will give you an idea how this can be done. Okay, to start with, let me introduce a very simple recurrence relation. Let's consider the sequence A0, A1, A2, A3 and so on, which is defined recursively as follows. A0 is defined as 1. Subsequently, for n greater than or equal to 1, I am defining an as 3 times the previous term of the sequence plus 2 times n. Now, this is for all n greater than or equal to 1. Let us see, we call this a linear recurrence because these coefficients, linear recurrence with constant coefficients, and this is actually non-homogeneous because there is something coming here. Anyway, these terms will be introduced to you in the next section, and in the next section you will also see mechanical ways of solving such linear recurrences with constant coefficients. In this section, I want to give you a justification why those mechanical procedures work. Okay. In any case, without further ado, let me directly go to the methodology. So this is the simple recurrence. The first term is 1. Subsequently, every term is 3 times the previous term plus 2 times the current value of n. Okay. So first few terms of the sequence are A0 is anyway 1, A1 is 3 times 1 plus 2, which is 5, A2 is 3 times previous term plus 2 times 2, 19, A3 is 3 times 19 plus 2 times 3, 63, A4 is 3 times 63 plus 2 times 4, 197. So it looks like this AN sequence is growing pretty fast. Okay. We will see why this is happening. Anyway, so keep this in mind. AN is 3AN minus 1 plus 2N for all n greater than or equal to 1, whereas A0 is 1. Okay. Okay. So now I will look at the generating function of this sequence. Now, when I talk about generating function without any qualification, I am always referring to ordinary generating functions, not exponential generating functions. So, the ordinary generating function or the generating function of this sequence is something like this. A0 plus A1x plus A2x square plus A3x cube and so on. Okay. Now, what I will do, A0 is 1, I know. A1 can be written in terms of A0 and something. A2 can be written in terms of A1 and something. A3 can be written in terms of A2 and something. In general, AN can be written as in terms of AN minus 1 and plus some other additive term. So, let me do this substitution. A0 is 1, this is 3A0 plus 2 times 1x plus 3A1 plus 2 times 2x square and so on. In general, this is okay. I think this is a mistake. It should be 3. Let's correct it. 3an minus 1 plus 2n. Okay. So I make only one substitution. And then you see that something has happened. You can see the same sequence appearing here, A0, A1, A2, A3, An minus 1. Only the coefficient of x is slightly different, but that doesn't matter because we will eventually absorb 1x. Okay, so if I just club together this term, this term, this term, this term in one expression, and the remaining things, this, another expression. So this in another, this in another, this in another, and so on. This will look like the following. First, I take 3x common, then I have a0 plus a1x plus a2x square plus a3x cube and so on in general. This is an minus 1 x power n minus 1, so the nth term will be an xn. And if I club together 2x, then I have 1 plus 2x plus 3x square and so on. Okay, if I take 2x common, this is 1 plus 2x plus 3x square plus this. This is nothing but ax itself, right? So, I can simply substitute this infinite sum by ax, and this I know is the expansion of 1 over 1 minus x whole square. So, I can simplify this as 1 plus 3x ax plus 2x over 1 minus x whole square. Now, if I bring ax to that side, this term, and do some simple manipulation, I see that this ax can be written as 1 over 1 minus 3x, that is coming from this, and 1 minus 3x will be common to ax. So, 2x, 1 minus x whole square, 1 minus 3x. So, using this trick, I have generated or obtained the generating function of ax of this series, this sequence a0, a1, a2, a3 and so on. And this is a nice closed form formula. Okay. Now, in order to expand this, I use a trick that should be familiar to you. So, remember this. This is 1 over 1 minus 3x plus 2x over 1 minus x whole square, 1 minus 3x. And this can be written as a over 1 minus 3x plus b over 1 minus x plus c over 1 minus x whole square for some constant terms or constant values a, b and c. Now, how do I determine this a, b and c? I multiply everything by this denominator, which in this case is 1 minus x whole square, 1 minus 3x. So, this gives me 1 minus x square plus 2x equal to a times 1 minus x square, b times 1 minus x 1 minus 3x plus c times 1 minus 3x. So, this is a standard trick. And then if I put x equal to 1/3, I will get the value of a. If I put x equal to 1, I will get the value of c. For this b, I need to equate some coefficient. Okay, so let us see what happens. So, put x equal to 1/3, this gives me the value of a as 5/2. Do these simple calculations. Next, if I put x equal to 1, I get the value of c like this, which is minus 1. Finally, if I equate the coefficient of, let's say, constant term a plus b plus c is 1. Okay, so 1 is coming from here 1, 1a, 1b, 1c. Therefore, we have already got the value of a and c. Substituting, we get the value of b as minus half. Okay. Okay, so given this, I now have a very clean looking expression for AX. 5 by 2 over 1 minus 3x minus half 1 minus x minus 1 minus x whole square. Now I can expand each of these things one by one. Let us do it. First thing is this, 1 plus 3x plus c square x square plus 3 cube x cube and so on. Next one is minus half times 1 plus x square and so on. Third one is minus 1 plus 2x plus 3x square and so on. Okay. Now if I take the coefficient of x power n from this side, I get the value of an, and that turns out to be, in this example, from here 5 by 2 times 3 power n minus half times 1, and here minus n plus 1. And if I simplify this a little bit, this turns out to be 5 by 2 times 3 power n minus n minus 3 by 2, and this formula is valid for all n greater than equal to 0. In particular, you can put these values n equal to 0. This will be 5 by 2. This will not be there. 5 by 2 minus 3 by 2, which is 1. So a0 is 1. You can check. Okay, so I leave it to you. Check that this formula is correctly computed. Just checks for small values of n. Okay. Whether this is giving the correct result. Fine. So using this trick, I could generate an explicit closed form formula for an for all values of n greater than equal to 0. So we will see a couple of more complicated examples. First, let us revisit our old friend Fibonacci numbers. So f0 is 1, 0, f1 is 1, and for n greater than equal to 2, fn minus 1 plus fn plus 2. Sorry, fn equal to fn minus 1 plus fn minus 2 for all n greater than equal to 2. Okay. So, this is once again, you see, a linear recurrence. Coefficients are constant, 1 and 1. And there is no plus term here. So, this is called a homogeneous equation. Anyway, more about this is coming in the next section. Let me now look at the ordinary generating function of this sequence, fn. This will be like this, f0 plus f1x plus f2x square plus f3x cube and so on. The nth term is fn x power n. Okay. Now what I will do, I will put f0 equal to 0 here and f1 equal to 1 here and write f2 as f1 plus f0, f3 as f2 plus f1, in general fn as fn minus 1 plus fn minus 2 for all n greater than equal to 2. But I will make the substitution once and only once from the second term onward. Okay. These are just initial conditions. So I cannot make any substitution here apart from this explicit value 0 and 1. Okay. So let me do it and see how it looks like. Okay. So f0 is 0, f1 is 1, so 1x, then f2 is replaced as f1 plus f0, f3 as f2 plus f1, f3 as, okay, f4 as f3 plus f2, in general this. So once again you see that the sequence is appearing twice. f1, f2, f3, f4, fn minus 1. Of course, f0 is missing here. but that is just one term. And here you see another occurrence of the sequence f0, f1, f2, f3 and so on up to fn minus 2 and so on. Okay. So if I club together these things with an appropriate adjustment of this x, okay, f1 x, f2 x square, f3 x cube, fn minus 1 xn minus 1. So if I take one x common from the first and x square common in the second, this sequence will once again surface. In the first case, of course, f0 is missing, so I can add and subtract f0 in order to complete that thing. So this was like this. So f1 x square, f2 x cube and so on. From second, f0 x square, f1 x cube plus this. And since this is homogeneous, no other thing. Now if I take one x common, this will look more familiar. Okay, I have not yet taken one x common, so just I introduce f0 here and subtract it here so that we do not have any problem. Value remains the same, the expression remains the same, and here of course it is starting from f0 itself, so I do not require any adjustment like this. So this will be this. Now this is once again the original sequence with just one extra power of x. This is also the same as fx with two extra powers of x. So I can take one x common from this and one x square common from this in order to write this as this and the second one as this. Okay. But this is my f of x. This is again f of x. So this simplifies to x plus x fx plus x square fx. Now if I transpose this and this to this side and make some simple manipulations, I eventually derive at this formula fx equal to x over 1 minus x square. Okay. So this is the generating functions of fx. Now somehow I have to expand this in order to obtain an explicit formula for the nth Fibonacci number. Okay. So I would like to write the denominator in the form 1 minus alpha x, 1 minus beta x, okay, instead of x minus alpha, x minus beta. It's not good. This form is better for power series expansion. We have seen already several examples of this type of denominators. So I essentially have to solve a quadratic equation, but that involves the opposite of this polynomial, that is y square minus y minus 1 equal to 0. Okay. So instead of solving this, I will solve the opposite, y square minus y minus 1 equal to 0. And now I can use the standard minus b plus minus root over b square minus 4ac whole by 2a, that formula, to obtain the two roots as alpha equal to 1 plus root 5 by 2 and beta equal to 1 minus root 5 by 2. In fact, you may know that this is called the golden ratio. Okay, this is called the golden ratio. This is the alpha is the golden ratio. And this is beta is just the conjugate of this. Anyway, whatever alpha is, the roots are this. So I now have fx equal to x over this quantity. This is now 1 minus alpha x, 1 minus beta x. This can be expanded as a over 1 minus alpha x plus b over 1 minus beta x for some constant a and b. multiply this everything by 1 minus alpha x, 1 minus beta x, you will get x equal to a times 1 minus beta x plus b times 1 minus alpha x, and then you put x equal to 1 over alpha so that this term vanishes, and you get the value of capital A. And if you put x equal to 1 over beta, this will vanish, you will get the value of b, and you see that this works out as a equal to 1 over alpha over 1 minus beta over alpha, 1 over alpha minus beta, which is 1 over root 5, and beta will come to, b will come to 1 over beta, 1 minus alpha by beta, that is 1 over beta minus alpha, that is 1 minus 1 over root 5. Okay, these are simple calculations. So now I have therefore fx, I can take this common, 1 over root 5, 1 minus 1 over minus alpha x minus 1 over 1 minus beta x. Now I can expand this and this into their infinite series. Okay. So, power series expansion therefore will give fn equal to 1 over root 5 whole times alpha power n minus beta power n. Okay, so you do this power series expansion. This is 1 plus alpha x plus alpha square x square plus alpha cube x cube. This is similar, 1 plus beta x plus beta square x square and so on, but I have a minus sign here, so it is this. So if I now substitute the value of alpha and beta, fn is equal to this. So this is our first explicit derivation of a formula, a closed form formula of the nth Fibonacci number. Okay. Once again, it is instructive to put or plug in small values of n and check that f0, f1, f2, f3, f4, all these are coming exactly as they should be. Okay. Fine. So, using the theory of generating functions, we could derive something which we could not do so far, namely an explicit closed form expression for the nth Fibonacci number. Okay. So, in order to demonstrate this general methodology, I take a final and third example of linear recurrence, but it is more complicated because each term is dependent upon 3 previous terms, although in a linear manner. Moreover, this is non-homogeneous, so some extra term will be there. So let's define this third sequence this way. Let's say b0 is 1, b1 is 2, b2 is 3, and subsequently bn is sum of the previous 2 terms minus the previous third previous term plus something like 4. Okay. So each term depends on 3 previous terms. Therefore, to start with, I require 3 initial conditions. Here I arbitrarily took these are 1, 2 and 3. Okay, it could be anything, any 3 constant values. Okay. So, now I want to find an explicit formula for Bn. Okay. So, once again I use the theory of generating functions, but before doing that, let us see first few examples of the terms of the sequence. A few other terms are b3, for example. This is this plus 2 minus 1 plus 4, 8. b4 is 8 plus 3 minus 2 plus 4, 13. b5 is 13 plus 8 minus 3 plus 4, 22. b6 is 22 plus 13 minus 8 plus 4, 31, and so on. So this is not growing so rapidly. The earlier both Fibonacci numbers and the first sequence, they are growing pretty rapidly because there is something called rho power n, this alpha power n, and there we have 3 power n in the first example, but here we will not have something like that. We will see anyway. Okay, so this sequence will grow like this. So as usual, I will look at the ordinary generating function of Bn. Okay, so it's something like this. Now B0, B1 and B2 are constant. After that, B3 I will substitute in terms of B0, B1, B2 or B2, B1, B0. B4 in terms of B3, B2 and B1. In general, Bn in terms of Bn minus 1, Bn minus 2 and Bn minus 3. So let us do it and see what happens. Okay, so it's something like this. This is 1, this is 2, this is 3. Okay. So, you see that again this sequence is reappearing in 3 positions. This, although it starts from B2, B0 and B1 are missing, but this is also an occurrence of this sequence. B2, B3, B4, B5, B6. Here you see you are getting another occurrence of the sequence, although it is starting from 3 minus 2, B1, B2, B3, and this is anyway the third occurrence of the sequence. This time it starts from okay, use this time it is starting from B0, B1, B2. Okay, so let me rewrite this. Okay. So if I take one x common, then this and this become same. If I take 2x common, x square common from all the terms of the second, n minus 2, n minus 2. If I take x cube common, n minus 3, n minus 3. But note that this is starting from n equal to 3, that is b2. So b0 and b1x are missing. So to do little bit of adjustment, readjustment, so I can write this as bx, the first 2 terms are missing, minus b0 minus b1x. This is starting from b1, 3 minus 2 is 1, so only b0 is missing. So it is bx minus b0, and this is anyway starting from 0, so nothing is missing, like this. Okay, now these are some small things. I substitute b0 equal to 1, b0 equal to 1 and b1 equal to 2, and eventually simplify this in this form. Okay, so small typo. So this 1 plus is extra here anyway. So just forget that. Then I push this on this side and simplify this to get this 1 plus x. This portion simplifies to 1 plus x. This is this. And then I have 4x cube over 1 minus x. And therefore, if I plug it in here, if I transpose it in that side and simplify this, it will look like 1 minus x square plus 4x cube over 1 minus x, this 1 minus x is there, plus 1 minus x square plus x cube will come. And if you see, this factors as 1 minus x times 1 minus x square. Once again, I can write that 1 minus x square as 1 minus x 1 plus x. So this is the explicit factorization of the denominator. Then I use the standard trick. This will be something like a over 1 minus x plus b over 1 minus x square plus c over 1 minus x cube plus d over 1 plus x. Okay. For some constant a, b, c and d, which I need to determine by giving some values to x, okay, or equating coefficients from two sides. Okay. First I clear the denominator. I get this equal to this. If I plug in x equal to 1, I will get the value of a. No, I will get the value of c. Okay. This is 1 minus x free. And if I put x equal to minus 1, I will get the value d. Okay, this is the only term which is 1 plus x free. Okay, and this gives c equal to 2. Put x equal to minus 1, and you get d equal to half, minus half. And the rest you have to obtain by comparing coefficients. For example, coefficient of x cube, this is 4. 4 x cube, this will contribute x cube. 1a, okay. This will not contribute x cube, this will not contribute, this will contribute minus d. Yeah. So, then you solve for a because d is known, 7 by 2. Finally, maybe I will look at the constant term. Okay, this is 1 here, and this will be a plus b plus c plus d here. So, but I have already got c, d and a, so I can obtain the value of b as minus 4. So now I have an explicit decomposition of this in this nice form. Okay. So I have 7 by 2 for this. Now each of these things I can expand using known formulas. Let us do it. This is just summation x power n. This is 2, so this is n plus 1 x power n. This is 3, so this is n plus 1 n plus 2 by 2 factorial. And this is also like this, except that this is plus, so minus 1 power n will come here. Now if I equate the coefficient of, or collect all the coefficient of coefficients of x power n from this 4 series, I will get the value of Pn as, here it is 1, from here I will get minus 4n plus 1, here I will get this 2 and 2 factorial, they cancel, n plus 1 n plus 2, minus half, minus 1 power n. And if I make a little bit of simplification, this eventually works out as n square minus n plus 3 by 2 minus half minus 1 power n. Okay, so unless there is a calculation mistake, this is the correct expression for Bn. So once again you can verify by plugging in small values of n, like 0, 1, 2, 3. Okay. So, generating functions can therefore be used for solving such so-called linear recurrences, homogeneous or non-homogeneous. Okay. But as I told you earlier, once again let me repeat that, there is a more mechanical procedure to be introduced in the next chapter for solving this. You do not have to play with this. Eventually, you will generate this kind of things much more easily than doing these calculation tricks. Okay. But again, I say that this exposition gives you a justification of that mechanical procedure. Okay. In fact, from where is this n square and n coming? That time, you keep this example in mind. This is very carefully chosen. The n square and n, from where are they coming? Here it is coming like this, from this. Otherwise, in the mechanical procedure, from where this n comes. Okay, anyway. So when you study those things, you will understand. Let us not worry too much about this now. So I end this lecture with a final example which is no longer a linear recurrence. Therefore, the tricks that you will learn in the next chapter do not apply to solving such recurrences. Now, apparently, generating functions is a more powerful tool for solving this recurrence. So, these are another of our old friends, that is Catalan numbers. So, in some earlier lecture, I have deduced a recurrence relation for Catalan numbers like this. So far, we have actually used C of n as a function of n, but for I would say, conformity with the other sequences that we are dealing with in this chapter, let us write the nth Catalan number as C subscript n instead of C of n. Okay. So in this notation, I have C0 equal to 1, and for n greater than equal to 1, I have this recurrence relation. C0, Cn minus 1, C1, Cn minus 2, up to all the way up to n minus 1, C0. Now, because 2C functions, 2C terms or 2C things, Ci, Cj are multiplied here, this is not a linear recurrence. Moreover, oh sorry, I made a mistake again. Sorry, this is not C1, this is considered as C, consider this as C, not C1, this is Cn. Cn is this, for n greater than equal to 1. Okay, fine. So in this third lecture, there are quite a few typos. Sorry. Anyway, so this is Cn. So let me correct it once again. Cn. Anyway, it will vanish soon. The generating function of this series is C0 plus C1x plus C2x square plus C3x cube and so on. Now I put C0 equal to 1. And for n greater than equal to 1, I will use this recurrence. Cn equal to this. Okay. What does it give? 1. And this is C0, C0. This is C0, C1 plus C1, C0. Next one is C0, C2, C1, C1, C2, C0. In general, I have C0, Cn minus 1, C1, Cn minus 2 and so on. Okay. Now you see that this is nothing but a convolution of the sequence with itself. Only one extra x is here. Okay. Other than that, it is just the convolution of this with itself. Okay. Therefore, if I take x common, this is nothing but this times this. Okay. Which generates the convolution. This. Okay. So, I have now derived Cx equal to 1 plus x C of x whole square. This is C of x, this is C of x. Okay. So, now this involves a quadratic equation in C of x. Okay. This is no longer a linear equation. So, what is that equation? Let me write it clearly. X Cx whole square minus Cx plus 1. Okay, although apparently it does not make any numerical sense here, but it still makes formal sense. I can use the same old quadratic equation solver, minus b plus minus root over b square minus 4ac by whole by 2a, in order to generate or in order to obtain the value of c of x as this 1 plus minus 1 minus 4x over 2x, x, 2x. Okay. Now question is, which value of which which radical or which sign shall I take, plus or minus? You see that if you take plus, 1 is there, this infinite expansion of this will give you another 1 here, and therefore you will end up with a term called 1 over x. But cx does not contain such a term. Okay. So, the choice of plus in the numerator gives a term 1 over x in cx. Therefore, the actual correct expression of cx is 1 minus root over 1 minus 4x over 2x. Okay. Now, if I look at expansion of this using the generalized binomial theorem, so this is nothing but 1 minus 4x whole to the power half. Okay. If I expand that, and then if I see that the 2 is appearing here, so whatever you have from here, okay, to divide that by 2, moreover there is one x here, so instead of considering the coefficient of x power n, you will consider the coefficient of x power n plus 1. Okay. Then that will give me the nth Catalan number in a purely algebraic way. Okay. We have already reduced a formula for this in a combinatorial way, but we will now get an algebraic way of reducing formula for c, nth Catalan number, and let us see what it comes. So, if you just look at this, before going to the next slide, let me, so what will be my nth, n plus 1th term? This is half, so half minus 1, half minus 2, up to half minus n minus 1 plus 1, so minus n will be there. From here I get 1 minus, and you will have n plus 1 factorial here. Moreover, this is not x, this is 4x, okay, and this is minus 4. So, I will have another minus 4 to the power n plus 1, okay. So, this is correct, right? Yes, minus 4 from this will come, n plus 1 factorial because it's n plus 1th term, and I have this general thing, minus half, sorry, this is not minus half, plus half. Beyond this everything will become negative. Plus half, this is plus half, okay. So, let me simplify this expression. So, I have minus 4 power n plus 1. I wrote n plus 1, right? Okay. That is, yeah, n plus 1. Oh, there is another minus here. Sorry, there is another minus here. So, I have to have another minus here. Okay. Okay. Just very complicated thing. So, minus 4 whole power n plus 1, 1 over 2x. So, half should be there. Again, I think I forgot that 2. Yes. It's 2 I forgot. So, 2 should be there. Yeah. So, finally, I believe this is correct. Minus 4 power n plus 1, half minus 1, half minus 2, up to a half minus n and n plus 1 factorial. Okay, so this is positive, but from this point, this is minus half, this is minus 3 by 2, this is minus 5 by 2, and so on up to minus 2n minus 1 whole by 2. Okay. So how many negative terms are there? N. So minus 1 power n, I just take out. Minus 1 power n. Then I just have 1 times 3 times 5 times 2n minus 1 n plus 1 factorial. And I have taken minus 1s and minus n plus 1 times this or this, n plus 1. How many halves are there? This is 2, 2, 2, n plus 1 times plus here 1, 2. 2 power n plus 2. Now you see that this and this essentially cancel. This is minus 1 per 2n plus 2, 2n plus 2 is even. And this is 4 power n plus 1, that is 2 power 2n plus 2. Out of this 2 power n plus 2 is there, only 2 power n remains. Okay. So this simplifies to 2 power n times this quantity. Okay. Now I multiply both the numerator and the denominator by n factorial. Okay. Now this n factorial as I write as 1 times 2 times 3 times 4 up to n. And I absorb one factor of 2 in each of this. So that now becomes 2 times 4 times 6 times 8 up to 2n, right? So n factorial with each factor absorbing a power of 2. This is 2 times 4 times 6 times 2n. And then what is the numerator? This is 2n factorial. 1, 2, 3, 4, 5, 6. So this is 2n factorial. And this n plus 1 factorial, I can take out 1n plus 1, n factorial times n factorial. So now I have, this is 1 over n plus 1 times 2n choose n. This is the same formula as we have derived using a combinatorial argument. Okay. And so essentially that's it. Okay. Even using a fully mechanical or algebraic procedure, I can derive a formula for the nth Catalan number. Okay. Using completely algebraic tools. Okay. So that is nice. So I hope I understand that you now grow some confidence in the usefulness of generating functions for solving a variety of counting problems and solving of recurrence relations. These are definitely going to be very, very important in computer science for analysis of algorithms, particularly the recursive ones and many other things. But anyway, let me stop at this point. I think this is good enough of a study of an introductory study of generating functions. We will study other different things in the later chapters. Okay, so until then, goodbye. See you.